do the logic design initially, and subsequently we have to follow the physical design and the analysis and verification for everything. So logic design in the case we need to create the schematic and schematic capture and variance and reuse and FPGA integration. So this comes under the logic design. So physical design case, we have to have the PCB layout and component placement, interactive routing, auto routing, manufacturing preparation, files preparation, so etc. It will come. So analysis side, we'll be having the simulation part like analog simulation, mixed AD simulations, HDL simulations, and signal integrity. So these three blocks consist of the complete system level design. And for the EDA tool, we need to clearly have the two symbols like logical and the physical symbol. So any EDA tool, if you take, you have to have the two symbols like logical symbol, which represents the logical pin connections of the particular component, and the physical symbol has the actual component size information representation of a component. So there will be three kinds of libraries like schematic library and the PCB footprint library and the 3D model. Nowadays, the 3D model of the component also is included in the library. So all three together called a common library. So the common library consists of three subcategories. One is the schematic library, second is the PCB footprint library, and the 3D model of the component. So main roles and tasks involved in the PCB design process are, in the case of engineering side, we need to clearly plan the floor plan. That is how much components can be accommodated in the particular given size of the boards, and how can interface the signals, what is the speed of the signal, and what are the power and requirements for the devices which is implemented in the circuit. And in case of RF circuitry, we need to have the clear layout technologies to be implemented, and what if scenarios, and other electrical connections, signal integrity. And in the case of product side, we need to verify with the EM verification and technical drawings, bus planning, high speed, power, and RF. So everything together makes the complete PCB design for process. So all these things has to be considered. And in the case of design flow, it will be like this. Like from the schematic capture, it goes to the PCB layout, and the PCB layout to the actual board manufacturing. So we need to have the schematic capture with these components. That is this op-amp or ICs or capacitors or resistors can be inserted from the schematic library, and this has to be translated to the PCB layout with the footprints as a component here. The footprints has the PCB layout library, which has the actual size of the component. So we can see this is the logical side, this is the physical side, and this is the actual board after production. So what is schematic? The schematic is a diagram which shows the interconnection between the components as per your circuit diagram. So you must have defined applications. So based on your applications, you have arrived the circuit for the thing. So for example, if you are designing the DC-DC converter, you have the circuit, and you have the circuit has to be simulated in the circuit simulators. And after that, you have to finalize the circuit for the particular workable model, and the circuit has to be drawn in the schematic editor. So this is a schematic, is a symbol representation, that is connection representation of this electrical connection between the components, and the components are represented by the symbols and the conductors. And so for each component, you will have the designator. The same designator is transferred from the schematic editor to the layout editor. So before you begin to the layout of your PCB, you must have a complete accurate schematic diagram. So after drawing the schematic diagram, you have to clearly check the connectivity So these connections, if you are making the error in the connections, so the same error is translated to the PCB, and you will get the end up with the error, board error. And the good practice will have the signals flowing from the inputs at the left to the outputs on the right. And your schematic really should be drawn with the PCB design in mind. So how the connectors will be placed, where the connectors will be placed, and where the, in case of Arduino, if you are playing with the Arduino kind of thing, so where the it has to be placed. So everything you have to keep in mind and draw the schematic. And the netlist concept comes here is in the schematic side. So in between you are making the wire connections, right? So that wire connection is called the connectivity information. So the tool understand the connection information as net. So see here in the below the notepad, you can see the net information. So A1 is a name of the net, where the J1 dot 11, so the component J1, 11th pin of component J1, and the second pin of U2, the 13th pin of U2 component is connected. Similarly, so with this same net, the other U1, U13, U16 components are also connected. So one complete information, one complete same signal is called a net, which is generated out of the schematic editor. And normally in the editor, we have the things called grid. So this grid is used for the placing, and aesthetic point of view, you will have the neat layout. And so sometimes it helps to for the routing and placing the components. And so a normal PCB designer will normally used with the help with the presence of grid. So you have to switch on the grid for the neat layout and other work. And so from last slides, we see the logical connections, the schematic thing. So the subsequent thing is we need to find out the actual parts of the component. So where do we get this actual property? So the manufacturers release the data sheet of or catalogs of each product. It is each component. For example, DigiKey so releases all the maximum components where you can see the so for example here it is metal film resistors dimensions is shown here. Here the body width is 6.5, and the lead size and lead width, length also is given. So based on this value, you need to create the footprint library. So as a thing, as we discussed, so there will be two editors in the EDA tool. One is schematic editor and a PCB editor, where these editors will access the components from the library, that is component library. It is called as a component library. So this component library will have the two parts, the schematic symbol and the PCB symbol, and the 3D model of the PCB symbol also is included with this component library. So the component library will be accessed by both schematic editor and the PCB editor. So one component, so for example, 74LSD-S00 is a component, one of the component. So this component has the two informations, like the logical and the physical informations with the same number. So this can be accessed by the schematic editor as well as the PCB editor. So you can see the individual symbol is here presented here. So this is inserted just directly from the library, and we can make the connections between the components like this. So this is called the schematic of the circuit. So this can be done in the schematic editor. So this connections establishes the net information. So from here to pin number 1 of capacitor and pin number 1 of this FB4. So this makes the same connections. This establishes the net connection. So this is translated to the layout editor. So similarly, wires are you can see we can use the ports, like instead of wires we can use like port information. So this port, so you can see the labels, net labels are connected here. So for example, the pin number 44 is named here ADD0. So the same connections, if you want to make it in a different another component, you can just name the same, for example, another component like transistors you are using or relays you are using in the nearby. So you don't want to make the wired connections. Instead of that, you can make the label, so it understands that those connections are same, provided you have to give the clear name same as the same pin number 44. So tool understands like so these both are the same connected together. So before you start the layout, we need to look for various parameters, like what is the minimum and maximum hole size of the thing, and minimum PCB trace width and separation. So current carrying, based on the current carrying capacities, you need to decide the trace width. And the maximum clearances. Clearances means copper to copper distance, and the maximum board size. So this depends upon the product designer and the product engineer, and the limitations concerning the board shape and other things. So required file format. Mostly we use the file as Gerber file. So this is this will not have the complete intelligence of the design information. So it will have the connectivity informations and the shape information, which is very much enough for doing the manufacturing the board. So these considerations has to be done before planning this board layout. And once you decide the board layout, I mean the schematic layout, you can follow this flow, PCB design flow, like the environmental setup and the netlist input and the placement and the routing, post process, and Gerber and cam view. So these are all the process we can follow for this PCB design flow. So we'll see one by one in brief. So first you need to prepare the footprint. So already you have the clear schematic editor, means schematic done, and after that you have to transfer the schematic informations to the PCB layout, right? So this before doing the PCB layout, we have to have the PCB footprints for doing this design. So for that you need to access the complete information about the component detail, like component data, component manufacturer's data sheet. So from there you can get the different kinds of information, like component size, shape, height, and volume, everything we will get. So these, based on this, you can clearly create the footprints. So as we discussed in the previous slide, so each and every component has two symbols at least, that is schematic symbol and PCB symbol, of course with this 3D model. So these three combined together is called, these three are correlated together is called a component library. So this component library will have only one name, like 74 whatever you give the name, and this name can be addressed for the schematic symbol and the PCB symbol as well as 3D, and this is accessed by both the editors. But schematic editor will have the access only for the schematic symbol, and the PCB editor will have access for this PCB footprint. So footprint is nothing but an actual representation of the component. So after making the connection, after making the schematic layout and after checking, you will have to translate the informations, all the informations, that is circuit informations, to the PCB editor by a simple click of the button in EDA tool. So where you will have the prior to that, you have already created the footprint of this all the components which is involved in the circuit, right? So netlist and board template, that is which gives a rack scissor. So this rubber band lines gives the connection information between the components, which is done in the schematic editor. So I hope this is clear for you. So this is nothing but the connection information, which is the tool is indicating us for making the connections between the components. So you can see this is component footprints, and this is a board outline. So this is the board. So which board outline. So where you have to you have to place all these components within this board size. And this red yellow color line shows the rubber band line shows the rack's nest or connection information from the which is taken from the schematic editor. So after placing all the components, the board within the board outline, it looks like this. So for this, we have many criteria like digital components and analog components should be separated each other, and the RF frequency components should should not be close to this high frequency speed high frequency packages. And similarly, the LEDs and other connectors part should be easily accessible to the thing, so that we have to place those components which is with the very proximity to the board outline. And the power delivery network has to be taken care. So all this, so various small factors are to be considered for placing the components and as well as the routing. And so for the power and ground distributions, we can have, so there may be multiple powers and multiple grounds, like analog and digital grounds will be there. And so to address those thing in the PCB, we can have an option for like power planes, plane kind of things. That is, a power planes is nothing but a copper port, which can be that port can be connected to the particular ground or power, for example 3.3 volt or 1.5 1.8 volt. So you can see the different shapes here. So this particular shape is considered as a 1.8 volt copper port. So in between two, between two powers, there will be a separation line, which is not a copper area. So that that separates the between powers between 3.3 and 1.8. So similarly, this same concept can be applied for the ground plane also. So the distribution of the ground should be continuous and for the proper return current. So this typical 4-layer stack up is shown here. Normally, in between signals, we introduce the ground plane or the power plane for making the return path perfect. And so this distribution of the power can be for in case of fine pitch components like DGA or thing. So we have to introduce the fan out vias for making the connectivity between the ground pads. So this shows the top and bottom side of the component PCB, which is after routing the thing. So as I said, the placing the component plays a major role. So various techniques has to be adopted for the placing the components based on the frequency, that is from the low to high. So we have to separate the components based on the frequency in the while placement of the component. So I'll skip these things. So definitely the decoupling caps of the IC pins, it has to be proximity to the power and ground pins of the IC to address the immediate power requirement. And in case of the return planes, the return signal, in case of low frequency path, it uses the low inductance path, I mean a low resistance path. But in the case of high frequency, it uses the low inductance path. So the discontinuities should not be there in the uh, 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 in the planes, which is proximity to the signal plane. So that is the low frequency return current definitely will take the least resistance path, like as shown in this figure. But in the case of high frequency, it takes the from the driver to the receiver, and the receiver to the driver will take the low inductance path, least inductance path. So the discontinuities of the ground plane should not be there. Otherwise, it will lead to the noise. It will introduce a noise such as the conducted emission and subsequently the radiated emission. And the placing the signal. So depending upon the current rating, we use, so for example, 0.3 amps, we use the 0.01 inch, that is 10 mil trace width we'll use. So in case of power and ground, if you are not using the power, using the planes, so you can use as a thicker width, like 0.05 amps, I mean 0.05 inch for 2 amps and other thing. And between the traces, that is making the connect between the signals, you need to have the clear separation. Otherwise, what will happen, you will get the crosstalk while in the operation side. And subsequently, you have to clear the clean up the silk screen layer. That is, the text should be legible enough to identify the component, and it has to be addressed for the top and bottom layers. In case if you are mounting the components in the bottom layer, so the bottom silk has to be mirrored, so that after manufacturing you'll get the clear text in the uh, bottom silk. And in case of the assembly drawing, so you will need to create another layer called assembly drawing, where the assembling of where it is printed and it is used for the while assembling process, where you will have the clear uh, component designation information for doing the assembly. So orientation information as well as the silk designation information will be present in this assembly layer. And of course, finally, the solder mask layer also, it has to be considered. The solder mask is completely non-conductive material, which is coated on the top and the bottom layer. So the mask should not be poured on the pads. That is, the pads are the access points where we mount the components, like, right? So so if you coat the mask over the copper pads, you will get the shock. You cannot solder the pins. So you will have to have the clear opening on the pad side. So other rest of the portions can be masked. So finally, you have the output. You have to take the output like Gerber formats. As I said, the Gerber format is the text information where you will get the X and Y location informations and the size informations of the copper drawings which you have drawn in the PCB layout. And then and drill informations also you need to provide separately for drilling. After the manufacturing, they'll drill the board. So for separately, you need to give the drill information. So that is the end of the process, and we'll go as for a demonstration of a PCB tool. So till now, if you have any doubt, I can answer. So this is a Design Spark tool, which is an open source. You can download without any. You can use it without any license. And so, shall I proceed, or if you have any doubts, 1 or 2 minutes I can explain further.
So respected professors, if you have any clarifications so far.
Any doubts in the chat side, sir? I couldn't see the chat.
Not it, ma'am.
Okay.
I'll intimate you if there is any.
Yes, sir. So shall I proceed the demonstration, sir? Okay. So this is the Design Spark, which is RS, which is released by the RS Components company. And so after opening the tool, you have this file, view, and settings like. So for creating a new project for the PCB, designing the PCB, you have to do file, new, and new project. So this is a project based design environment. So you have to create the project first, and then you have to create the schematic design for the schematic editor and the PCB design, and this for the PCB design. So initially we need to create a project. So I'll create a folder for this particular demonstration. So I'll browse. The project name is I'll do a sample. So .trj file under this directory is going to be created if you press OK. So this is the project window which we see here, and here you can have all the other accessory informations for editing or other details. So from here you need to create initially you have to create a library, right? So for the library you need to pick the library button. So as I said earlier, so you have various tabs here. One is schematic symbols. The second is the PCB symbols. The schematic symbol is a logical representation. PCB symbol is a physical representation, actual component dimensions. And the third is the component library. So these first two tabs are integrated together to form this component library. And the 3D view is attached to this component, which is default libraries are also there. And if you want to include your component, you can add as a step file of the component, and you can integrate this. So the main access point is the component tab, where you have the integration between this schematic symbols and the PCB symbols. So let me try to create one sample in each library. So I will create one. So using this first, I will create the schematic symbols. So using this wizard button. So where it will ask for the various informations like technology, type, styles, and pins information. And after that, the process will get completed. And so then if you press the next, it will ask the technology and units you want to use. So here I'll do the as it is. That is, I select the unit as with the 3 decimal precision values. And after the next type is you want to have either the rectangle or the rectangle with 4 sides, or the segment. So depending upon your logical connections, you can choose the thing. So right as of now, I choose. I'll try to create an LED component, and I press next. So these default values I can leave as it is. So for LED, leaded component I'm going to create. So I have the pins on left is 1, pins on right is 1. So so this is correct. So I leave like as it is. So here I am going to give the name of the symbol. The symbol means logical representation. Okay, so it is going to save. It is once it is created, it will be saved in this particular demo schematic. So the library name is the demo schematic library, where the LED is going to be stored in a particular thing. So if I just get press with the finish, it will create into the library. So you can see the demo. You can see the demo schematic has one more component it is included, which is LED. So in the same case, like PCB symbols, I'm going to create another LED for the footprint, like actual component values. So for this also, under this PCB symbol tab, I'm going to use the wizard button, and we are going to press the next. So technology, we can leave it as it is, and the type. So you can choose whatever you package you want to use is can be selected. Like suppose if I am using the LED as a chip cap, this chip components, ceramic components, we can select this, or if it is a through hole component, I can select this type of thing, dip component. Like you can see the pad counts is actually 2, so you can so this modification can be seen in the view window, and you can play around with these values. Like after watching the data sheets, like component manufacturer's data sheet, you can give the pin to pin informations. Like so it is everything is self-explanatory. Like pin to pin pitch is E, so you can enter the pin to pin pitch here after seeing the data sheet. So right now I'm following this default value which is present here. And so here also I will you can see the notch. For some components there will be in the creation of ICs, there will be a notch on the component for making the orientation, right? So for that case, you can select the notch, or some cases for there will be the dot informations like pad 1. So this dot informations can be see here it is actually overlapping. So after creating, we can edit, we can modify these values, and we can change whatever as it is necessary. And for LED, I think if you have any like anode, cathode, or diode information, so whatever information, so pin number 1 indication, whatever you need to indicate, so it has to be indicated after creating the component. So once the base component is created, so whatever extra cosmetics can be added to it. So here also the same LED name I am giving. So we right now we have created 2 components. There is schematic symbols and the PCB symbols. Schematic symbols is the physical representation, the logical representation, and the physical representation can be LED. Okay, so after creating the schematic symbols and the PCB symbols, we are going to create a component, actual component. So here also I am selecting the wizard. Okay, so next, pressing next. So if you want to, if you have the RS number, so RS components is the owner of this tool. So they are providing the component component. They are dealer of the component. So if you know that, if you want to order the components from the RS number, you can give the number. Otherwise, you can leave it as it is. So I am going to create the same component where the package is through hole, and this, since this is the LED, so the default reference can be L. So if you are increasing the if you are placing the 4 numbers of components of the same type, so it will automatically creates the L1, L2, L3, L4, like so. That is the reason I give the default reference value here. And if it is a resistor, you have to give as R, so that R1, R2, R3, like that, it will be incrementing. And the components, number of pins in the components 2, number of gates in the its default is 1. And here you have to select the schematic symbol. So we have created the LED here, like, and next, sorry, you have to go to the corresponding schematic library. Otherwise, you'll mislead to this thing. So this is LED we have created. So next, and similarly, I have to go to the demo schematic. So here also I have created the LED. So this is the flow actually given in the left side. So we have to give the details and the schematic, select the schematic symbol and select the PCB symbol and assign the pins. So assigning the pins means both the schematic symbol and the PCB symbol has 2 pins, right? So pin number 1 of the schematic symbol should be assigned to the pin number 1 of the PCB symbol. Then only the connection information will get transferred to the PCB layer. So for this purpose, we are assigning the pins. So see, you can see it is empty. The schematic terminal numbers 1 and 2 has to be assigned to the pin number 1 and 2 respectively. So if you are assigning 1 to 1, it is default. By default, it will allocate the pin number 1 to pin number 1 of the schematics footprint symbol. So if you want to change the anything, you can very well change according to your need. And it asks us for the saving the component. So it's finished. So here also you will get the LED light. So based on this flow, we can create the library manager. So I have already created some of the components in the library for making. We can have a schematic trigger like any circuit we can take. So for first we need to. So as of now, I have created the libraries alone. So after that, I have to create new. Already I have created a project, right? So we have to create a schematic design. So for that, also we have to select the and give the name appropriately. So the schematic, if you press OK, you will get the schematic editor here. So this is the editor, schematic editor. Here you can see one.sch is added to this project. And if you go to this tab, you can see the schematic editor. Where see this is the dot. This dot represents the grid of the thing. So you can change the grid by using the grid values. And before that, I would like to use this unit as unit with 3 decimal precision. So and after that I can set the grid value. So grid value can be 0.1. So this is not a standard one, so you can use according to your necessity. So you can see the grid on the screen. And some of the other features are listed here. So you can save and open, you can save this component and you can open the library and you can edit the after placing the components, and you can see the property of each components. And view side, you can go to the colors. So you can change the colors whatever you want to have, and you can add, if you want to add the rectangle or close shape, a circle, whatever you want to have, you can according to your schematic requirement you can add. And preference side, there is setting side, you can have the design technology where each and individual parameters of the PCB designs can be set here. That is pad style, and text style, and line style, connection side. So normal width can be set here. If you want to change, you can change. And nets. So once after completing the connections, you can see we will see the design technology tab, how it looks like. So there can be three net classes: signal, power, and ground category. So ground is considered as a power category. So both these are comes under the plain thing. And tools, you can update the components from the component library. This option is used to translate the schematic to the PCB, and you can check and can forward the design changes, can back annotate, and some of the design calculators are available for trace width and resistance things. So you can play and track impedance, you can calculate and via resistance too. So various tools can be accessed using this design calculators tab. So currently I'm going to place the component, that is add the components to the schematic editor. So for example, I am going to insert a component by using the add component tab. So this will pop up the add component tab, where you have the various folders of the library. So you have to clearly select your library. So I have used this demo component library. So in this library, I have some few components here. So I am selecting the 555 timer here. So you can see I have given the designator as U, but it comes as a U1. So initial thing is U1. So suppose if you are copying this component, either you can use Control C or edit copy. So it has come, the reference designator has come as U2. So as of now, I will select only, I will have only U1. And after the thing, we have the capacitor. Capacitor C1. So 2 capacitors I have inserted, and again this depends on your circuit only. So for the aesthetic point of view, I am rotating this by one step thing. So by selecting the component, I can right click and rotate the whatever angle you want to have. So right now I will select only resistors, and I'll connect the by select. You can just move or move by selecting the thing, move and drag by selecting the components, and with the help of the mouse. And you have to here, this is the logical representation of the component. So just I am randomly making the connections between the components for your understanding. So I just double click the connections and just press just leave the thing to the into mark, or otherwise I can use the sketch connections or add schematic connections. So both are the same functionalities. So double click and I leave these connections for making the node kind of things. So for here also I am So I'll have these connections as NC connection. There is no connect connection. So I can insert ground. So this becomes a ground connection. So if you drag, you can drag the component. Suppose if you want to have another component to be inserted here, you can drag very well using the mouse button. So the connection information will not will not be affected because of this drag. The connection information remains the same. So similarly, I can add a power supply. VCC power supply. This is a random circuit. I'm just making it for your for the demo purpose. So I think the connection, if the connections are over, we have to can check the reports kind. So you can select the bill of material and dangling connections. Like if there are any dangling connections, that is open connections, it will indicate for the thing. So these checks can be done. Unconnected pins and schematic check, so netlist. So all these connections information reports can be generated out of this schematic. And after this, the design technology, you can see under the nets. So you can see the ground connections, that is under the ground connection has the ground class. It automatically takes as a ground class, VCC as a power, and other connections as a signal. So there are other 3 signal nets connections which is placed in this schematic. So I am ready to translate this to the PCB area. So here I just press the translate to PCB. It will ask for the another window, like it asks for the again the unit. So can select the mm with 3 decimal units. And it asks for the single layer or double layer board. So just as of now, I press the double layer board, and it will ask for the board information. Either it can be circle, or if it is a circle, you have to give the dimensions, diameter information. Or if it is not a circle, you have to give the width and the high length information. So I select as maybe 100 mm, 50 mm by 50 mm, 50 mm. This is the board outline information, and we can give the sample as name as a sample, PCB name as a sample, and finish. So this net signal classes has to be defined in the schematic itself. So you can see the board outline for 50 mm by 50 mm has already has been created, and the other components which is inside this schematic editor has been translated to this editor. So this rubber band lines makes the shows the connections which assist the routing process. So I think this board size is bigger, actually bigger compared to this component. Since we have only 5 components, so we can directly drag and keep this component, and we can reduce the board size. Okay, then so if you can see, you can just press and drag based on your connection information. You can press, you can drag it. So you can see the connections of this 2 pins comes in the below. So I am placing this component here, and for the ease of connections, I am rotating this to 90 degree. So still it is giving the cross connection. So 180 degree I can shift, so that I am getting this correct information. So in between I get I have this these connections too. So I am rotating this to 90 degrees. So some of these numbers are visible, right? So that can be disabled by right clicking the properties, disable the pin numbers, and pin names so that it will not get disappeared. I mean, it will not be disappeared in the layout side. It will be disappeared. Similarly for others. Okay, so you can see again, you can rotate. This should be okay. So this is U1 is representing this timer component, and see, this is R1, this is R2 is resistor component, and C1 is other capacitor component. So C2 is the other capacitor. So this can be rotated based on the aesthetic point of this. This is actually the silk text, or this comes under the silk layer. So to make the uniformity, so I have rotated this C2 direction to 180 degrees. Similarly, R1 also can be rotated. So that symmetry can be followed. So we can leave it as it is. So if you want to reduce the board outline still, you can reduce. Now it is time to do the connections. So before that, you have to here also in this editor also you have the design technology where various styles and line tracks styles, everything will be available. So you can introduce whatever things you want to have, and spacing also. So track you can do the settings like track to track spacing should be 0.254 mm. So based on this value, the tool will generate the reports. If it is not to 0.254, it will get the violation report. And rules, the minimum trace width I have set here is 0.05. It's a default value, so 0.05 I will set. Just apply. Okay. And if you just by double clicking the rubber band line, you will get this trace information. After completing the trace, you will, this rubber band line that starts next will get disappears. Or you can choose the add track option, and you can make the connection. So I am just selecting the trace, and you are you can, I think you can see the perfect angle between the signal flow. So otherwise, if you're using the I mean acute angle or other things, you will end up with the signal issues. So otherwise, you just double click the you can see the space between this thing is very minimal. So between the components is very minimal, so I cannot do the 45-degree angle. So I am for as of now I am putting this as 90 degrees. Actually, we need to move the components and make the space for making the connection. So if you take this property of this trace, you can see this is routed in the top copper, and the net and everything informations are given here. So here I cannot route in the this trace. There is this selected trace which is shown in the white color. So this is actually a ground trace, and this is a signal trace which I cannot route in the top layer, right? So for that purpose, I am using the second layer, that is the bottom layer, for making the connection. So I make right click and next layer. So you can see the color change of the next layer. So for this purpose, adding via, so making the connection. So the top and bottom layers are connected through this via, and this is actually a signal layer. So this is also I am going to route in the bottom layer. So bottom layer connections can be shown in the different layers. So this, if you see this property of this trace, you will get it is a will get to know it is a bottom layer. And this color informations can be saved using this color tab. So where you can set for top, bottom, and other silk screen, and for every layers you can set as color to clearly identify the layer names. So this is a ground signal. So the ground can be I thought of pouring this into as a ground copper, that is ground as a plane. Instead of routing the trace, I am going to use this ground copper. So for that I am adding the area, so like rectangle, right click, pour copper. So this is the copper plane, which is I'm switching off this copper, bottom copper, so that you can get the clear idea. Okay, so this component is actually a signal layer, but surrounding the signal layer you will have the copper core which is connected to the ground. Okay, so you can see the ground. So you can see the ground pin, that is ground part of this portions, like capacitor C1 second pin, and the first pin of IC, and the sister pin R1, like so. These three pins are connected to the copper port, brown copper port. So this green color indicates this connection between this land, that is pad, and the ground connection. So similar, this is the plain concept which is used for this PCB. And after completing the PCBs, and you can use the I mean, before that thing, you can use a design rule check, where you can run the spacing between, suppose for example, you can select the tracks. Between tracks you need to check the spacing, right? So you have, if there is a spacing error, it will indicate this here. So from that you can access the error point, and you can make the changes and rerun the design rule check. So similarly, for all the checks you can perform, and you can after performing the thing, you can generate the reports out of the bill of materials, like whatever components you are used in the design, so which can be used for the purchasing, and you can release it for the your clients or so. And after that, you can finally do the manufacturing plots. So these are all the layers available for this PCB, that and you can export this is in the Gerber format. The Gerber format is a universal format which is used for the manufacturing the board. And you can, if you run the thing, you will get the text file, like with all the, this is the log file which has all the information related to that. The file which is stored, the project which is stored in the folder, will get the all the information related to the Gerber formats. So you can see in this time it is generated the copper information. So these are all the Gerber file format. So these things can be zipped together, and we can forward it to this manufacturing industries for the production. And in case of if you want to view this component in the 3D view, you can just view the component in 3D. So this is the approximate default component which is taken by default in the by the tool. So if you want, if you have the specific 3D step file, you can very well import with this, integrate with this library, and you can do the connections. I mean, you can view the thing. So that 3D views are mainly used for in case the components are touching each other, or the volume of the component is, the land size can be very small, but the volume can be very big. So if you, and the height restrictions can be there. So to have the clear 3-dimensional view, it will be better to have this 3D thing. So you can see the bottom side of the PCB. So one trace we have routed in the bottom side. So this is the bottom side. So you can see the ground connections are connected with this copper plane. Okay, so with this, I would like to conclude my demonstration. So if you have any doubts, I'm okay, ready to answer the question. What are nets and power plane? Nets are the signals, actually, Akash, and nets can be the same signal from one pin to whatever pin it connects. So one signal can pass to many components like capacitor, resistor, or relays, whatever it may be. So the same signal is considered as a net. As a net, and the power planes are the as a copper pole, which is as a ground plane I have poured, right? So that is actually a plane concept. So instead of making the trace connections, we are connecting this as a plane. So actually, if you see, so this is actually a ground pin. So this can be this has to be connected to this pin. Actually, this is ground, and this is also ground. So instead of making the trace connections, I am pouring this as a copper, and this copper is connected, the copper pore is connected to this particular connection. So this is called a plane concept. So this plane has many advantages in it. So that will be a separate topic. So as of now, the plane is connected to the plane is for making the connection between the components. So that is the concept. So any other doubts?
Professors, if you have any clarifications, please requesting to unmute yourself and interact with our session, ma'am. Chat box is open for queries. Feedback link has been posted in the chat box. So kindly put your valuable feedback. Even if you have any queries, you can raise your queries in the feedback also. Later it shall be shared with our session, ma'am. Ma'am, kindly share your PowerPoint so that we shall
Sure,
share
sir.
at the end of the program.
Sure, sir.
Thank you, ma'am, for accepting our invite. Despite of your busy schedule, you have accepted our invite, and thank you for it. And on behalf of GRG Polytechnic College and Instrumentation Control Engineering, we render our heartfelt gratitude for sharing your expertise throughout our day. And if you have any clarifications, especially participants, if you have any clarifications, you can have your clarifications over here. Ma'am, you shall Really a great session by Piyush sir. It was a great session.
Thank you, sir. Thank you for the management for inviting me, and thank you, participants, for having me invited here. And I really, since it is a big area, so I just focus and confine myself to particular things to explain this in three and a half hours. So for if you want to have in depth details or any other things, I'm okay to explain in detail with the given thing. So thank you everybody for this session.
Ma'am, if you have an official email address, you please share in chat box.
Yes, sir.
Email address and the contact number has been shared. Dear professors, kindly have an eye on the chat box. Ma'am has posted a mail address and official contact number. Feedback link has been posted. Kindly fill your valuable feedback. And I request all the professors to resume back the same meeting ID and password by 1:45 p.m. For the second session of today. Thank you. Thank you for being with us. And thank you, ma'am, for spending your full day with us. Thank you.
Thank you so much, sir. Thank you, sir.